This is 500 watts off-grid solar powered irrigation system. This is the project that I'm working on as in my thesis research. This project has been divided into 3 different divisions. The first one is the power production or the solar production. That includes these 2 solar panels, 250 watts each. And we have this solar tracker or solar translator that tracks sun from east to west facing southwards. The location is Dayton, Ohio. The weather is partly cloudy, or sometimes we get overcast. So today we are not going to get the optimum performance. The second part of this project is the diagnostics or data acquisition system that includes several sensors to analyze or evaluate the performance of any kind of renewable energy. This is a pyranometer. It sends or measures the radiation from sun, and based on this you can evaluate how much the solar radiation is falling on these 2 solar panels. Let's go and check the second and third part of this project. This is the data acquisition board or data acquisition system that contains several sensors. These are the 4 current sensors for different devices. For example, one for panel 1, another for panel 2, and the third one is for the energy storage, and the 4th one for the pump. And then we have voltage transducers varying voltage from these devices for panel 1, panel 2, energy storage and pump. And we have these 4 thermocouples or the temperature sensors that are measuring temperature for panel 1, panel 2 for energy storage, and the outside air temperature or the ambient temperature. And other than that, in the diagnostic or the data acquisition system, we have one flow rate meter that measures the flow rate of the pump, and the pressure sensor that pressure at inlet and outlet. The third part, that's the irrigation or the pumping system, that includes this 80 watts 24 volts DC pump, the tubings, the irrigation fluids, etc. For energy storage, we have got 2 batteries, 100 amps hour each, so they are connected in series, so it makes it 24 volt system. That's what required by this 24 volts DC pump. And we have got this MPPT charge controller or maximum power point tracking device. So it performs 2 different operations. The first one is it prevents the overflow of charge or the current coming from the panels to the batteries, so it protects the batteries from the overflowing. And the second part of this MPPT is to steps down the voltage and increase the current. So in this way you will have more current flowing into your batteries from the panels, so overall you are increasing your efficiency of the system. These are 2 solar switches. One is for solar, another for the batteries. This is the timer for the pump. It's automatically like starts or turn on the pump and turn off the pump. So idea of this whole project is to design any kind of data acquisition or diagnostic system that can analyze or evaluate the performance of this whole project. So this is what I've designed, and you can connect any kind of renewable energy power, either solar or wind, connected to this data acquisition system, and it would give you the performance parameters, that how much the power is being produced by your renewable energy system. And I use the National Instruments data acquisition cards. These are 2 data acquisition cards, DAC. So they take the readings or they take the data sensed by these sensors, and it's acquired by these 2 devices, data acquisition card, and that data is sent to the LabVIEW platform. I'll brief you shortly what's the LabVIEW platform. Let's go and check the reading section or the LabVIEW. So this is the virtual instrument that I designed in LabVIEW. I've designed in such a way that all the parameters or all the sensors that I showed you in the data acquisition system, they acquired the data or they sense the data, send it to the data acquisition card, and data acquisition card send it to the LabVIEW. And here we have this all. So this is a reading coming from the pyranometer. That's a sensor that was connected to the pyranometer or to the solar. So right now we are getting almost 941 watts per square meter. The maximum solar radiation you can get at any part of the world is almost 1050. So it's not 1050 right now, but sometimes I get 1050. And similarly, we have the readings coming from these 4 thermocouples, the temperature sensors. They are all showing the same reading, 22 Celsius. It's because they are all at the same place. By this you can actually evaluate what's the effect if the temperature increases. If there's an increase in temperature of the battery, how does it reflect in the performance of the panels? Similarly, if the ambient temperature increases by a certain value, what's the performance of solar radiation or the solar panels? This is the section for the pressure inlet outlet, and this is the flow rate meter from the pump. How much is the flow rate? It's 3.1 gallon per minute right now. And then we have divided the voltage, current and the power for each of these devices. For example, this is for the panel 1. So the panel 1 is producing 26 volts and it's producing 5.6 amps, and right now the power produced by one of these panels is 145 approximately. And this is the readings. This is the reading from the panel 2. This is the voltage from panel 2, that's 26. Current is 5.7 amps, and the power produced by this panel is almost 150 watts. And this is for the battery bank or the energy storage, how much the battery bank is charging that voltage. It's 24 volts right now. The current coming to the panel from panel 1 and panel 2, current coming to the battery is actually 11 amps. And this is the total power that's being stored in the battery. It's almost 280. And this is the section for the pump. So right now it's drawing 24 volts and current is 1.5 amps, and the power consumed by this pump is 40 watts approximately. So I hope you like my project, and I'm working in a wind tunnel lab, Wright State. Thank you for watching my video.